Hello and welcome to our final webinar of the year. This lesson is to be watched before 5:16. And basically what we're doing is we're going to be solving systems, and you have done this before. You did this in Algebra 1. And so first thing we need to do is describe what a system is. And a system is two equations with two unknowns. And so basically we have like something like 2x plus 3y equals 7 would be one equation, and the other equation could be something like 3x plus 4y equals 19. And that's a system. If we go to solve these, we can find out what both equations, but both x and y are. We can find out where they intersect and things like that, find out where they meet. An example of a non-system would be something where you have more than, so if you had something like 2x plus 3z equals 9, and 5x plus 2y equals -3, something like that. And not having the same variables would be an example of a non-system. There are three ways to go about and solve these linear systems, and basically one of them is by graphing, and we'll talk about that. Another is called substitution, and the final one is elimination. So elimination is the last one. And so there's three ways to go about it. It doesn't matter which one. You just need to be good at one of them, and you can always get through it. Some of them take longer than others. Some of them are better than others. So let's go through some examples now. So the first one, it says, let's solve it by graphing. Well, if you look, this is just a standard y equals equation. So I'd start up 2, and my slope is up 1 over 1. And this one is x equals -3. So I would get a graph that looks something like this. And so the solution of this system is basically where these guys cross, and it looks like it is at -3, -1. And that's really what we're looking for. Where are the two graphs crossing? Well, if we do it by substitution, if we have the equation y equals x plus 2 and x equals -3, we could just plug in what x is. We already know that the ordered pair for x is -3 where they cross. If I plug -3 in and simplify that, I would get y equals -3 plus 2, which means y has to be -1. And so you can see from the graph, that's where they intersected, and from substitution, that is also. So substitution is a valid way, plugging in one equation into the other. Now this one, they give us these two equations, and if you were going to solve them, you're probably going to have to make sure you get the equation in y equals form. So I'm going to add y across the equal sign for both equations, just so that I can get it alone and make it positive, and then I will subtract 3 for this top one and add 3. So I would end up with an equation for the top one that y equals x minus 3, and the bottom equation, it looks like it would be y equals 7x plus 3. And so now if I was to graph these, you could see this equation is the 7x plus 3. There's the positive 3, and if you look at the slope from down here, 1, 2, 3, 4, 5, 6, 7, and over 1. And this equation was crossing at -3, up 1 over 1. There's the slope for that equation. So there's the two graphs, and it looks like from the graphs that when these two guys cross, I'm at -1, -4. So if I want to do it by elimination, what you do is you stack the two equations on top of each other, just like this, and you pick one equation, and you take the equations, and if you can add them straight down and something eliminates one of the variables, the whole idea is let's get rid of one of the variables. If I add straight down, I get 8x plus or minus 2y equals 0, which doesn't eliminate one of the variables, so there's really nothing I can do there. That doesn't help me, so I don't want that. What I really need to do is I need to change the signs, multiply everything by -1. And if I multiply everything by -1, my equation, the top equation, will remain the same. And the reason I multiply by -1 is that when I do this, you'll notice that my y's change signs, and now I have different signs. So it didn't matter. I could have gotten rid of the x's if I wanted. The top I would have had to multiply by -7. But it was easier to multiply by -1, so that's what I did. Now if I add straight down, I get -6x. The y's cancel each other out, and that equals 6. So now if I solve algebraically by dividing by 6, -6, x will come out to be -1, which we already knew from over here. You can see it. It's right there. There's -1. Now, if I want to find the y value, I can plug this -1 back into one of the equations, one of the originals, or any of them actually will work. But I'm going to plug it into the top one. Just seems like it's a better way to go. We had x minus y equals 3, so I now substitute -1 in for x. And solve, if I add 1 across the equal sign, I end up with -y equals 4, and so I have to divide by -1, and so y comes out to be -4, which we already knew from the graph, but this is another way to go about it. Now we can solve this one just by graphing, and if I was going to solve it by graphing, again I would have to get at y equals, so I'm going to subtract 8x on the top equation from both sides, and so now I have y equals -8x minus 4, and on the bottom equation I am going to add the y across the equal sign because that makes it positive, and it makes it exactly the same on both sides, so now I have y equals -8x minus 4. Well, with that, you'll notice the two equations are exactly the same, so when I graph them, they get the same line. And when you graph and get the same line over and over again, you have infinite amount of solutions. And so, since they have an infinite amount of solutions, because anywhere on those lines would be the same solution. It says over here, what would a no solution look like? Well, those would be parallel lines. Parallel lines will have no solutions because they never cross. And so when you have parallel lines, they're not going to cross. These guys are the same. So there's three options in this one. You either have one solution, which is what we had first. That's examples 1 and 2. 1 and 2. We have infinite amount of solutions. And that's example 3. And then there's also no solutions. No solutions which come up, there's no example for this, but comes up because of parallel lines. Alright, so that's basically what we're dealing with on this. So just remember those, you're going to need to know them. And then finally, when might we use this? Something like this. It says the English Club is selling poetry cards and bouquet of flowers for Mother's Day. The club obtains the cards for $2 and the bouquets for $3.50, but they're going to turn around and sell them for $6 and $8. The club will spend $360 and are expected to get $900 back. So if I set up a system for this, I'm going to set up one for how much they pay. So 2x, we don't know how many they're buying of those. We don't know how many they're buying of the bouquets. And actually, I'm going to change the variables just to make it a little bit better. So I'm going to say $2 for the cards plus $3.50 for the bouquets, and they're going to spend $360. The other equation is they're going to charge $6 for the cards and $8 for the bouquets, and they're going to hopefully make $900. So that's the system that we have, and we have a couple different ways we can go about this. We can do it by substitution, we can do it by elimination, we could graph them. If you graph, you just have to solve for one variable for each equation and then graph them on the xy plane, see where they cross. This one I'm actually going to do by elimination. I'm going to try to make my life a little bit easier, just because there's nothing really canceling out. I'm going to multiply the top up here. I'm going to get rid of the c's. So I'm going to multiply the top by -3. And when I multiply the top row by -3, I will get -6c plus, minus, it's going to be minus now, minus 10.5 b equals -1080, and then the bottom row will remain the same. 6c plus 8b will equal 900. And so now, if I go ahead and add straight down, you'll notice that the c's go away. Great. That's what elimination is all about. We want to get rid of them. Here we get a negative. It looks like 2.5 b will equal -180. or 100. Wait, hold on, I gotta learn to subtract here. Sorry about that. Let's try this again here. About 180. Or learn to write actually. Negative 180. And so now if I divide that by negative 2.5, divide both sides by negative 2.5, then I will get, so negative 180 divided by negative 2.5 equals 72. So what I found there is that I need 72 bouquets in order for this to work out. To make this amount of money, I need to sell 72. So then if I want to find out how many cards I need to sell, which is the other part of this, then I will substitute 72 back into either one of the above equations. I'm going to use the bottom one because it's all whole numbers. So 6c plus 8 times 72 will equal 900. All positives, nothing to worry about on that. So now if I go 8 times 72, that gets me 576. So then I have 6c plus 576 equals 900. And so if I subtract 576 across the equal sign, I will be left with 6c equals, wrong one, equals 900 minus 576 is positive 324. So we have 324 left over, and if I divide that by 6, which is what I'll do, divide by 6, then I get my final answer, divide by 6, that I needed 54 cards sold. So in order to make the profit that they need, I need to sell at least 54 cards and 72 bouquets. So that's our lesson on systems, and your out is to write down your favorite method. My favorite method is to do elimination. It's usually the quickest for me. Substitution works well. It just depends on, for your out, it depends on which one works best for you. So thank you for listening to my webinar. I hope you guys have a good summer, and I will talk to you soon.